And there's both the certificates. Good.
Nice.
That way, if they say, "Oh, you didn't do it," I got proof.
Mm-hmm. I don't
That's
think
happened once.
I don't think I did. I don't think I did it my sophomore year, and nothing happened. But
Eh, just in case, I don't want.
yeah,
There already has been stuff that's like, "Oh, nothing's going to happen," and then,
yeah,
like the time we were trying to pay for my using this college funds, trying to pay for these classes, and then didn't get there like till 2 months later after the classes started.
yep.
Mail.
I've had my payments delayed too, but not like because of our fault, because of other things, and then had to pay
Oh
late
yeah,
fees. And it's like,
it wasn't even it really wasn't even the mail's people's fault or all. Well, okay, the mail just couldn't get there. It wasn't really the college nor the trust fund's fault. It just the mail took that long.
yeah, whatever. So let's go ahead and hop into this. So just a reminder, what is a capacitor?
Oh God, this is the third time you asked that, and yet
I
I keep
know.
forgetting that.
The reason I keep asking is because I know it's going to help you.
Oh, I understand that. Uh, it just sucks that I don't have the definition all down in my head. And going to have to go back and look for that note. And I don't even remember where I put it. Well, the capacitor is supposed to be. Oh, wait. The ability to store the charge?
That's capacitance.
Alright, I keep mixing those two up.
Yeah, so what is a capacitor?
Let's see. Capacitance is the ability, so the capacitor is able to use it, I think.
So what sort of capacitors do we see?
Defibrillator. Right?
That's an example of capacitor, but like more specifically, the sort of questions you're seeing on your homework and whatnot in this class.
Oh. Oh, that type. Parallel plate.
Yep, exactly. Parallel plate capacitors. So what happens when you take a capacitor and you connect it to a battery?
Stores charge.
Mm-hmm.
Uh, one plate will be a positive charge, the other plate will be a negative charge, and then they will create an electric field in between.
Yep, exactly. And how do you relate the charge and the capacitance? The charge on each plate
Uh,
and the capacitance.
Capacitance equals to charge over the voltage.
Mm-hmm. Exactly. So does that charge on the capacitor appear instantly when you hook it up to the battery?
No.
What happens?
It takes time. It takes a long time for it to get all for the uh current to go through and store the charges. I believe. I think that's the right way of saying it.
So if we were to plot the charge on each plate of the capacitor as a function of time when we hook it up to the battery, what is that going to look like?
Oh, it's a graph.
Yep, so if we have like a graph here.
No, that's discharge. I want charge. So if as time increases, the charge will increase until it hit max charge
So
for a certain amount of time.
just something like this, and then it hits max charge.
I don't think I can see anything right now.
Oh wait, I'm dumb. Yeah, there we go. We up now. I was like, I completely forgot. Yo, how's it going, Sean?
Hey, what's up?
Nothing much. Don't have any specific problems prepped for this session, but we're just talking through the material and the concepts that you guys went over yesterday, and then hopefully you guys can have like some homework questions or discussion questions that you had issues with that we can go over.
I'm good.
So is this what our charge over time is going to look like when we hook it up to the battery?
No, it'll be more like a curve.
A curve, so something like this?
Other, no, the other direction.
The other direction, yeah. Oh. Ugh. So it's going to look something like this. And it's going to slowly approach a maximum value. Something like that. So, what is the equation for this curve? Like you know how we've had like 1 over x curves to describe, what's it called, isothermal curves for PV diagrams. What sort of curve is this?
Or say it, let me at least double check it. Nope, wasn't even that. So I honestly don't know.
If we're asymptotically approaching some asymptote here of the maximum charge, what sort of equations do we have that approach asymptotes?
Does this have to do with trig?
Nope, it's not trig.
Okay, then, because let's see. I know it's not like x squared or anything like that.
Has to do with one particular number, a certain constant that appears in almost everything.
Does this have to be like square roots?
Nope, there's no square root. It's very natural, you would say.
So logs
Which,
or natural logs like ln or logarithms.
yeah, it has something to do with the natural log, but it's not a natural log. What's the inverse of a natural log?
I actually don't remember that.
Ln.
Well, that is the natural log. You know how like you have like log base 10?
Yeah.
What is the natural log? What is the base of a natural log? You guys were just going over it yesterday in your lecture.
E?
E, exactly.
Oh, okay. There was E. Okay.
Yeah.
Okay.
So if we have e to the x, it's going to be just like an exponential increase up to infinity. If we have e to the negative x, it's going to asymptotically approach 0. So how could we represent this in terms of e in some sort of exponent? It's going to be a function of 1 minus e to the negative x. And in this case, x is time over a constant. So the charge is going to asymptotically approach a maximum value as a function of 1 minus e to the negative x. What about the current through our capacitor? What is the current over time going to look like?
It's going to be at max and then decrease all the way to 0 after a certain amount of time.
Yep. So what sort of function would that be?
Okay, so is this going to be the inverse of that of the previous equation, 1 minus e to the negative x? Like the other way?
It's just going to be e to the negative x.
Oh, okay, so it's just e. Oh, okay.
Yep. All of these capacitor charging and discharging equations are going to be some sort of an exponential here, where it's like e to the negative x, and it's going to be either e to the negative x if it's decaying, or it's going to be 1 minus e to the negative x if it's increasing up to a maximum value, exponentially approaching an asymptote.
Okay. Yeah, it's been a while since I have done those type of equations.
Yep.
Or at least see them in graph form.
So this is what happens when we hook a capacitor up to a battery. Now, what if, let's say we have a circuit that looks something like this. We have a battery over here, and then we have the capacitor, and we're also going to have a resistor. And let's say we then go ahead, we charge the capacitor up. It's been connected for a long time. First of all, what's going to happen if we go ahead and disconnect the battery?
The capacitor will start to lose that charge.
So at the exact moment we disconnect the battery, what does the capacitor look like?
At that exact moment, the charge should be max, and there shouldn't be a current.
Why wouldn't there be a current?
Well, I mean, at that moment. When it's zero, there shouldn't be, like, as soon as we do it, I don't think a current will be, but as soon as, like, probably after a second, a current will start moving.
I'm talking the exact moment after we disconnect the battery.
Oh, okay, then yeah, there will be a current. Sorry, yeah, the wording the wording of that you have to pay. I have to pay attention to that.
Yeah, sorry. I mean, like when I say at the moment we disconnect it, I mean like just after we've disconnected it.
Okay, then yes, there will be a current.
Mm-hmm.
It will be a small current, and then the current will just get stronger over time, till there will be no more charge.
How would the current get stronger over time? Aren't we going to eventually run out of charge?
I guess I'm thinking a little bit too much there.
So what does our capacitor effectively act like right after we disconnect the battery?
A battery.
Exactly. It acts like the battery itself. And so, but we know that eventually the capacitor is going to completely discharge. What is it going to look like after a very long time?
A wire, basically.
Mm-hmm. So if we just have, well, not a wire. That's what's going to happen. That has to do with when we initially hook it up to a battery.
Oh well, after a very long time, it will lose all its charge, so it won't act like a battery anymore. So I think it'd be more like a. No, that's not open circuit either. I don't know what you would call
it.
But...
you're right. It effectively acts like a wire. When it's completely discharged, it acts like a wire. So what's going to be the current in the circuit here after a very long time?
0.
Why is that?
Because there's no charge.
Exactly. There's no charge. There's no source of voltage or current or anything in the circuit. It's literally just a discharged capacitor that's sad and has lost all its charge. And then there's a resistor that's just sitting there chilling like, I'm not doing anything. So, but in between those two states, what does the charge over time look like? And what does the current over time look like?
So this is discharging, so... Well, honestly, the Q will have its max, and it will and it will decrease over time.
So, an exponential decay like this?
Yeah.
Mm-hmm.
And I think the current is the same, I believe.
Exactly. Both the current and the charge start at a maximum value, and they exponentially decrease to 0. So for a charge, if the capacitor is charging, the charge starts at 0 and exponentially increases a maximum. And the current starts at a maximum and exponentially decreases. For discharge, both start at a maximum and exponentially decrease to 0. That's pretty much all you need to know for capacitors and RC circuits. Because most of what you're going to see in this class is essentially, for RC circuits, is conceptually understanding what the capacitor is going to look like initially and after a long time when it's connected or disconnected from something. Do you guys have any specific examples you wanted to go over for the RC circuits, like from discussion or from homework? Anything that gave you guys trouble?
I haven't seen anything so far. I haven't really, not through discussion or class. Though I was trying to see if I could do the trick that you showed us for the matrix with the capacitors. I kind of got a little bit of it, and it just wasn't exact numbers. I was like, probably either you could or you can't do it.
You really wouldn't be able to, because, I mean, the charges and the currents and whatnot through the capacitors is changing over time.
I see.
So
okay, then
you could do it if you just had an example for a circuit where the capacitors had been connected for a long time, and you could be like, okay, well, because they're connected for a very long time. First of all, what's the current through a capacitor after it's been connected to a battery for a very long time?
0.
0, exactly. So what does it act like?
A wire. Oh, wait. After a long time. Hold up. The wire is initial.
Mm-hmm.
Hey,
Open circuit.
Sorry, guys. I think I might have to go. Me and my family are planning on going out to get lunch.
Yo, fuck yeah. Do it. Get some good food.
Yeah. I think we're going to get burgers.
Ooh, hell yeah. Get some cheese on it.
Oh, hell yeah, of course. Who gets burgers without cheese? That's fucking... I can't believe there are people who actually do that. It's just... I don't understand.
My sister does it. I don't understand.
It's...
She likes to pretend she's
weird.
She likes to pretend she's lactose intolerant, and then she'll go and eat mac and cheese.
Oh my god.
Alright. Thanks for stopping by, Sean.
Thanks.
Good luck studying.
See ya. Thanks.
Sorry to say this, but I eat hamburgers without cheese. Sorry.
Oh no! 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 You were just you were sitting there silent, like, ooh, crap! Oh crap! Oh crap!
It's just more. Hey, it's preference. That's really is it.
Yeah.
I just prefer to eat it without cheese. That really is it.
And some people have preference for getting vaccinated. Some people are just wrong. All right. So you didn't have any specific examples?
Yeah, not really.
right,
Honestly, this one didn't seem that tricky. Again, I'm going to have to kind of get used to thinking, oh, after a long time, it's going to be like an open circuit, so it's going to be this, versus, oh, we just did it right there, so it's going to be this and this.
Mm-hmm. So, ooh, this problem looks fun. So you were able to get this problem on the discussion yesterday, no problem?
I mean, it did take some thinking, but
So
eventually,
take me through the thought process. Like, you don't need to, talk specific numbers. Just like explain how you got each part.
Once I find all the papers, because some of these papers like to be blown around by the fan. And I don't find it. There it is. Alright, so problem 2.
So a circuit is constructed with 4 resistors, 1 capacitor and battery, and a switch as shown. The values for the resistors don't matter. Wait, he actually used values that weren't complete freaking garbage. Holy crap. Or I guess the other...
Yeah, it was nice for once.
The other value... I suppose the other values are always, like, randomly generated from Flip It, so...
Yeah.
Alright, so capacitance, battery
So-
voltage... Go ahead.
So, yeah, for I1, for I1 when I was looking at it, let's see, what was the magnitude of the current through the first for R1? Well, uh, basically, I just thought, well, if we're only focusing on R1, and then R1, it's going to be somewhat the same as us. The current of R1 will also be the same current as R4. So I just did the voltage over R1 plus R4, and it gives me 20 amps.
So why don't you take into consideration R2 and R3?
Uh, the the reason is during at let's see, what was it? The switch has been open and then the switch is closed. Okay, so this one got me a little bit too. Then when the TA say it, it's because to the current of R2 and R3, there's no current there. There's no flow.
So why wouldn't there be?
Um, I believe the current is going through the capacitor. I think the capacitor is taking all the current.
And why would that be? Is that going to be the case the whole time while it charges, or is it just initially?
That's what I'm still trying to get. Um, I think it's only as soon as it starts charging.
Exactly.
I think. Okay.
So now that you know that that's correct, try to explain why.
Hmm. Explaining why. Oh boy. Okay. So it will have the current going through it, but as times goes on, the current decreases. So then there'll be a starting of a flow of a current in R2 and R3.
Yep.
Okay.
I mean that's one way you can put it together. I mean, you see the current for the capacitor over time starts at a maximum and then decreases to zero, and you know that the current through, I mean, the total current through the battery would be relatively, no, I'm being dumb, but regardless, so you know the current is decreasing over time through the capacitor. That means some of the current is going to go through the resistors. Another way you can think of it is initially, when our switch is just initially closed, the capacitor acts like what?
Oh, initially closed. So a wire.
Exactly. So I'm just going to go ahead and redraw our circuit real quick. So essentially our circuit looks like this. We have the 4 resistors, and we have this path here that's just a wire. So what's the total resistance over here for this path? Whatever, 2, 3, 5 total ohms.
5.
What's the total resistance of this path?
None.
None. So all of the charge is going to go ahead, all the current in the circuit is going to go ahead and take the path of least resistance. Because there's no resistance through this path, it's all going to go down this path.
Of course it wants to take the easy way out.
Exactly. Yeah, they're like us students. So all the current is going to take the path of least resistance, and none of it is going to go through those 2 resistors. Initially, literally just for the first millisecond. And then slowly over time, the current is going to shift, and eventually what's going to happen after a very long time?
It will eventually just take the path of most resistance. It basically will not go through the capacitor anymore. There won't be no currents through the wire.
Exactly. So eventually, after a long time, the capacitor is here and it's fully charged, and it acts like an open circuit, so then all the current would go around the outside. So So you're right. As you know, initially I1 is whatever V over R2 plus R4, which you said was 20 amps. That's correct. And then I2 initially is 0. What is the voltage across the capacitor just after the switch is closed? How do you get the voltage across the capacitor just after the switch is closed?
The voltage should be the same voltage as did I even put weird. That the voltage should be definitely 0, I believe.
And why is that?
The voltage of the capacitor would equal the voltage of 2-3 of the resistance of the combined resistance of 2-3 because they're parallel to each other. And since there's no current in 2-3, it should be 0.
Yep. I mean, absolutely correct. That's one way you can think of it. Another way you can think of it is, what's the voltage drop through a wire?
Just initially at 0.
Yeah. If you go through a piece of empty wire, there is 0 voltage drop because there's 0 resistance.
Okay, so there was a simpler way of thinking about it, but
they're both
right.
Honestly, they're both equally simple. Whatever works, works. So, and then what would be the current through R1 after a long time?
That would be I1 is equal to the voltage over R2 for all the resistance in total. So, which would just be 10.
Yep, exactly.
10 amps.
10 amps, because the total resistance is 10 ohms. Now,
yes.
What about the charge on the capacitor after a very long time?
To get the charge, you need to take the capacitance times the voltage, and the voltage that we want is the voltage of 2-3.
Mm-hmm.
And whatever the voltage is, you have to, in order to get the voltage, you need to find the current and the resistance of 2-3. And then, what else did I say right there? Oh, and since we knew the current of I1 equals to the combination of I2 and I3. I1 was 10, so there could have been other ways to figure this out, but I2 and I3 had to equal each other since they were in series. So the only combination that would work, that would satisfy both the equations of I2 equals I3 and then I1 is equal to I2 and I3, I2 and I3 had to be 5 in order to make I1 10.
Hold up just a second, though. I think you just got yourself a bit confused. So you said that you're correct that I2 and I3 are equal.
Yes.
Are I2 and I3 both meeting at the junction with I1? Because you said something about I1 is equal to I2 plus I3. But where do all three of them meet at one junction?
Oh, I forgot to put that on my thing. I1 is equal to I2 3 because they are, when I am also taking the effect of the capacitor being parallel to to R2 and R3.
Mm-hmm. So then what's I2 3?
I2 3 should be I1.
Exactly. It's all just 10 amps all the way around the circuit.
Yeah, so I think I just did one step too many. But yeah, eventually it would just be...
So then what's the total voltage drop across the capacitor?
50.
Mm-hmm.
I believe. Yeah.
Yep.
And then since it was since he's using C as microfarads, I have to do 10 times to the -6 to get farads.
Yep. Not pharaons, farads.
Farads. So basically the final answer I have is 50 times 10 to the -6 farads.
Not farads, because our final answer should be in terms of charge.
Oh, sorry, charge. So coulombs.
Exactly. So it's 50 microcoulombs is the total charge on the capacitor. Because then after the switch has been closed for a very long time, we're going to go ahead and reopen it. How would we find the current through R3 immediately after the switch is opened? And what direction would it be in?
Oh, wait, did it say direction?
Yes.
Oh, forgot to put that part in there. Whoops.
So you can find the direction through R3 without, like, you don't need any numbers to find the direction. And in fact, you can calculate the numbers and actually find the magnitude, but that won't help you finding the direction. So let's find the direction first.
Yeah, so that's the one I didn't do. Okay. Well, I'm assuming that the current should be moving to the right. Oh wait, when R3, so it should be going down.
And why is that?
Okay, I'm gonna say since the capacitor has a since I'm trying to figure out the proper way to explain it by drawing the loops. So the capacitor on the top plate has a positive charge, and so by going and then it will want to end up at a negative charge. So the flow of the current should be going from the positive to the negative.
So
I believe that's
like that?
Oh, I was thinking the other way around.
Oh, you mean positive negative, like going all the way around like this?
Yes.
Mm-hmm.
That's what I was thinking about.
Yep, exactly. So it's like
Okay.
the capacitor acts like a battery where we have the positive terminal and the negative terminal, and the current flows through from positive to negative and around like that. Because the current in the circuit is the current. In actuality, current is a bunch of electrons usually. It's like electrons and holes of positive charge. I'm not going to confuse you with 400 level semiconductors talk. But basically, the charge is mostly actually a bunch of electrons moving. So it would be the electrons moving around like this. But we define our charge as the flow of positive charges, which is just opposite to the flow of negative charges. So the positive charges are repelled from the positive plate away and attracted to the negative plate towards, like this.
Okay, then.
And it's the same way for the capacitor. When the capacitor is disconnected, or when the battery is disconnected, so it's just the capacitor acts like its own battery with positive terminal, negative terminal, and the same direction applies. So, how do we find the magnitude of the current?
Well, that's going to be the voltage of 2 to 3, because we know that, and then over just the resistance of 3, which should just gives us 10 amps. Because the current of, in this case, I'm going to say the current of the I3 is the same current as I2.
Mm-hmm. Yep. Your logic is pretty sound. Because the voltage in the capacitor is still the same 50 volts from before, and 50 volts divided by the total resistance of our new loop, because these two resistors don't matter anymore. Total resistance 5 ohms.
Yeah, that last question did took me a while to try to figure out. Because I do know it's going to be, uh, the current is equal to V over R3. I was just like, what's our V? And then after staring at it a while, I was like, oh, our voltage still has not changed.
Yep. Voltage is still the exact same before and after the battery is disconnected. Like the moment before and the moment after.
Yeah, because I was just like, well, how do we determine it? And it was like, oh, it's the moment after, so the charge is still the same. The voltage is still the same.
Yep. Exactly. So it seems like you're actually pretty good with this whole RC circuit stuff.
Yeah, I have to pay attention to the wording.
Mm-hmm. Yeah, it's honestly one of the few conceptual things in this class that actually like can sort of be understood and make sense in my opinion, even though it's
As long as you didn't have trouble uh, with the electric currents beforehand.
yeah, but a lot of people do. But that's pretty much RC circuits. Literally, all you need to understand is, initially and after a very long time, after switches opening and closing, which isn't too overly complicated. And I guess you could also, bonus points, he might give you one question where it mentions something about how it charges or discharges, and it's going to be exponential increase or decrease or whatever. Now, the other thing you guys went over in class yesterday, what else did you guys go over?
Yeah, that's magnetism.
Magnetism. So, what is magnetism?
A magnet.
A magnet. Excellent. 12 out of 12. You're going to ace your quiz tomorrow.
Yeah, I know.
So, magnetic forces act similar to electric forces, right? But how are they different?
So let's see. Well, the magnetism for the I'm trying to make sure. Okay, magnetic field lines. They come out of the North Pole and go into the South Pole,
Mm-hmm.
and that's
that would,
always happen.
that sounds like it's pretty similar to an electric field where they go out of positive charges and into negative charges. So that's one way they're similar. Keep going.
Let's see. What else? The equation to figure out the magnetic force is equal to the charge times the velocity cross the magnetic field.
So, first things first, what the hell is a cross product?
Yeah, let's see. The cross product is supposed to be one moment. I believe it's A times B times cosine theta. If it's something along those lines.
You're close.
I know I'm close. I'm trying to find that one paper again. Why is this fan like to blow everything around? Oh, sine, other one.
Exactly. So, for
what
exactly, dot product. Cosine is the dot product. The cross product is sine. So, we have some sort of... That's how you get the magnitude. It's A times B times the sine of the angle between them. What about the direction? Because a dot product is a scalar quantity. It has no direction. A cross product is a vector. How do we find the direction?
The direction should be the magnetic force, I believe.
Mm-hmm. And so how do we find that direction?
The right-hand rule.
Describe the right-hand rule to me.
Let's see, where's that cheat sheet? Directions of the right-hand rule. First, point the fingers into the direction of the velocity. Then you curl the fingers in the direction of the magnet field. I almost said force field. And then point your thumb in the direction of the force.
Exactly.
And this is for positive charges. And if you're dealing with a negative charge, just flip your hand 180 degrees.
Yep.
Your right hand 180 degrees, if possible.
Yep. So if our magnetic field is going to the right... Oh, actually, first of all, what velocity are we talking about?
Speed?
Yeah, so of what?
Speed of the particle.
So if there's a particle in a magnetic field that isn't moving, what is the force on it?
Since it's 0, shouldn't the force be 0?
Does that make any sense? If you have a particle sitting in the magnetic field, it's not moving, that means there's no force acting on it?
Well, physics doesn't make sense.
You have learned well, young Padawan. You're right. There is no force because there's no velocity. So, if we have the velocity off to the right, and the magnetic field is downwards, so VB, what direction is the force going to be in?
I'm guessing left, if I did this right-hand rule correct.
To the left. Go through it step by step.
Well, the velocity, you have to point your hand toward the right.
Mm-hmm.
So you just move your hand to the right. Then you need to get your hands to curl downwards. So you move the palm to the field, and then you curl your hands to it, and then you point your thumbs out. And I'm guessing it's to the left. It's either left or into or out to the page, something like that.
So which one is it?
And that's what I'm still trying to figure out. That should be up, down, onto. No, this should be into, out to, right. Okay, so it should be left.
How would that make sense? Doesn't it have to be at a 90-degree angle to both V and B?
Yeah, so it needs to be perpendicular. So, maybe I'm not doing the. I think I'm gaining the velocity correctly. It's just the magnet field I'm probably messing up.
Yeah. Here, let's try something. Is this going to work? All right. Am I here? Yes, I think I am. This is working.
Yes,
cool.
I can see you.
Yeah, so basically, I'm going to try to do this. So if I'm pointing this direction, I think Discord flips it. So I'm pointing to your left, right?
Yes.
Okay. So I'm going to do this with my left hand, but for you it looks like my right hand, correct?
Okay. Yes.
Okay.
You're pointing on my right side.
Okay, exactly. How's it going, Todd? Going over right-hand rules right now, and things are a bit confusing. So actually, we point to the right with our velocity, right?
Yes.
And then we want to curl our middle finger down. So essentially, our palm is downward, and our middle finger and like all our other fingers curl down. And then my thumb is pointing into the page right here.
Oh, so that's the direction of into the page.
Yeah, exactly.
Jeez Louise, that's the issue. It's like figuring out which is left and which left and right and which one's into or out to the page at times.
Mm-hmm. Exactly. Right. Unfortunately, I can't do this webcam while also recording my screen for the session because I use OBS to get my webcam into Discord, but we can do that if we have any other issues with right-hand rule stuff. But yeah, unfortunately, there is no way to like do the right-hand rule. It's just practice and getting comfortable with being confident in your final answers.
Hooray.
So essentially, that's pretty much all you guys. I mean, yeah, that's the main thing you guys went over is magnetic forces, or the magnetic force with particles moving in an electric field in the direction of the magnetic force. So, what happens when you have the particle in a magnetic field? Like, let's say the magnetic field is large enough that the particle is constantly going to be inside it. Like, it's effectively an infinite field. If we just let the particle travel with a velocity, what's going to happen?
Wouldn't it cause the uniform magnetic field? Or am I thinking something else?
Well, the magnetic field is uniform. Essentially, the magnetic field is uniform and infinite. So
the motion of the charged vehicle. Okay.
Yeah, I want the motion of the charged particle. Let's say this is our magnetic field. It's infinitely large, and it's going. We'll say it's going into the page. And we have the particle traveling initially right here, and it's traveling to the right. What's going to happen?
It's going to curve. It's going to basically try to go into a circle.
Why is that? I mean, first of all, what direction is the initial force on the particle?
The force should be perpendicular to the velocity.
What direction?
Well, if it's going this way, it should be up.
Exactly. Initial force is upward. So our particle is going to go ahead and, because of the force on it, it's going to be moved sort of up like this. When it gets to this point, what direction is the force acting on it?
Perpendicular to the velocity again. So it would be up, upright. Oh wait, sorry, up left. Getting my left and rights mixed up.
Mm-hmm. And then it curves more. We get to here.
That would be to the right.
To the right?
Oh, sorry, left. Again, mixing up my left and rights again. That's the one thing I'm going to have to keep an eye on, too.
Yep. I must say, it really hurt me. One of my first, it was my first semester doing this class. It was back when it was in person. And I would sit in the lectures and they'd have their weekly quizzes every Friday. And it hurt me so much. I wasn't allowed to help people out. I'd be sitting there, and the two kids right next to me were both using their left hand and holding their pencil in their right hand while writing. And it was just like, oh no. Oh no, no, no.
Oh boy.
I just sat there like, oh. But yeah, that's pretty much it. We have the direction of our force is always perpendicular inward towards the center of this circle, and that's literally the recipe for uniform circular motion. It's like throwback to physics 121 with like a tension and a ball swinging around on a string, or like a gravitational orbit. A velocity and the force always perpendicular to the velocity. So it's going to except it's actually going to be a uniform circle and not this utter garbage I've drawn. I didn't go to art school, goddammit. So, how do we find the radius of this circular motion?
Oh, isn't that the... Let's see. Isn't that the centripetal acceleration? Well, I mean, that's one way to find it, I guess.
So go. What is the centripetal acceleration?
Velocity squared over the radius. Wait, is that velocity squared?
V squared over R? That sounds...
Yeah, V squared over R.
Exactly. Like, throwback to... Here, I can actually pull up the 121 formula sheet. If we wanted to look at it. I don't know if it actually gives that equation on the formula sheet. But...
Oh, it is the thing he did go over in class, and that's what he did say.
It was V squared over R, yeah. I'm trying to see what does it say here? Does it actually give it? Does it not give it anywhere? What? That's crazy. But yeah, it's V squared over R. The way I learned it back in my day was the force was mv squared over r, but obviously...
Yeah, that's what he did say. He had that too. And then another way to write it would be r is equal to the mass times velocity squared over the force net.
Yep. So mv squared over r, and so then the acceleration is v squared over r. So the force, mv squared over r, which we could write... How do we find the magnetic force again?
Oh, magnetic force. The charge times the velocity cross the magnetic field.
Yep, QV cross B. If we're assuming we're traveling perpendicular to the magnetic field, what does V cross B become?
Perpendicular, that means the sign is just 1, so it's just V times B.
Exactly. QVB sine theta. Sine theta is sine of 90 is 1. And then we just solve for R, right? R is equal to mv squared over qvb, so it becomes mv over qb.
Oh, okay.
And you have that.
Okay, so that is the... Okay, I thought the big R meant something else.
Yeah.
Sometimes radius... I always like to associate radius with little r, so...
I'm just keeping it consistent with what he has here in the formula sheet, which unfortunately... Unfortunately, I believe this is actually inconsistent with what he had earlier in the semester with Coulomb's law, right? Yeah, Coulomb's law, he had it in terms of little r.
Okay, so I better not confuse myself on that one and just say that's... put big R and just say that is also the radius.
Look, even here, in frickin' 2 classes, when you're going over Ampere's law, it goes back to little r. God damn it, Dr. G. Keep it consistent, please. You're confusing the students.
I mean, please. Yeah, that's what I always try to do, find consistency, because I always, when it comes to temperature and time, I always do time little t, temperature big T. Anything else, and if there's another T, I'm just going to make some fancy work, because there's no need to make 5 different T's.
Yeah, exactly. But that's pretty much all you need to understand for magnetic force for tomorrow. You just need to understand QV cross B. You need to know cross product is magnitude times the sign, and you need to understand how to use your right hand, not your left hand.
Yeah, I'm going to have fun with that right hand rule.
There's a joke we can make here, but I won't make it.
Oh, that's why.
So you guys have any other questions about this? All right.
Yeah, not really. I'm still getting into the RC circuit homework right now.
Yeah, we can go over one more quick little RC circuit homework problem, because you missed the beginning. We went over RC circuits and stuff real quick. Do you have a specific problem you want to go over? Because we still got 4 minutes technically.
I could use some help figuring out how to solve for the charge.
Yep. You want to pop? Yeah. You want to take a screenshot and put it in session text?
I mean, this is the one I'm working on now. It has 2 capacitors, and I have to find the charge on the second. but it's part of the Flip It Physics homework, so not sure if that's allowed.
I mean, you should be able to just. I mean, you should be able to just take a screenshot and post it. I mean, we've been doing that in every few sessions here, and plus people post the stuff, and you can also post it in the homework chat. Like just taking a screenshot of the question itself, it wouldn't be a problem.
I think I can cast my tab.
Oh yeah, you could do that too. You can screen share.
Yeah.
Oh, is this? Oh, I think I know what question she's trying to figure out. It should be one of those that everybody has the same one at that point.
Yeah, hold on. This is taking me a little bit of time.
All right.
Yeah, it is that.
Pop this out. All right. So we got switch S in the circuit shown below. It's been open for a very long time. And at time 0, it is closed. So it's asking for Q2 final, the charge on C2, after a long time after the switch is closed.
Yeah.
So first of all, what happens when the switch is initially closed?
Well, the current is going to flow through the circuit normally, and the capacitors are going to act as regular wires. So you just make everything a parallel. It'd just be a series and parallel circuit. Or well, you'd have to combine R2 and R3 because they're in parallel, and R1 and
Exactly.
make.
So what happens after a very long time?
Well, there will only be a current flowing through resistors R1 and R2 because the capacitors will be fully charged by then and no charge will flow across it.
So basically they act like open circuits?
Yeah.
Yeah, exactly. So what is the total current through the battery, or like through R1 and R2?
Looking at that, R1, R2, 330 divided by 12. So about 0.036 amps.
Sure, I'm going to trust that you got that right. I mean, because it's just divide R1 plus R2 into the voltage, which is 12 volts. So how do we get the voltage drop across our two capacitors?
The voltage drop, you use Q over C.
Do we know the charge?
We do not know the charge.
Exactly, so we can't use that. But that's what we're going to use to find the charge. So how do we get the voltage drop?
Well, I mean, it would be a parallel circuit, so the voltage should be the same.
As what?
As R2.
Exactly. What's the voltage drop across R2?
Voltage drop across R2 would be, I haven't gotten that far yet. Hold on. The 1 plus R2. Voltage R2 I have 8.
How did you get that?
I multiplied the total current across the I multiplied the total current across the circuit by 220 ohms, the resistance of R2.
Exactly. It's current times the resistance. So, is that the voltage drop across each capacitor, or is that the total voltage drop across both capacitors?
It's the total voltage drop across both capacitors.
Exactly. So, what do we know about the charge across a capacitor related to the voltage drop again?
Charge should be equal for each capacitor in series.
Exactly. So does that mean we can just solve for it as if it's just one capacitor? And wouldn't that could we just solve for that charge?
Yep, we could. You'd have to add it as a series capacitor though, so
How do we add capacitors in series?
you have to take the inverse of their inverses, of the sum of their inverses. In other
Exactly.
words, yeah.
1 over C1 plus 1 over C2, all that to the negative 1. Or, fun fact, another way you can do it is...
C1 times C2 over C1 plus
Exactly. Love it. So what is that total capacitance?
C2. C40, 80, 3,200 divided by 120.
Boom. It's about 26 and 2/3. 26.66.
Yep.
So what would be our total charge? Our Q final? How do we solve for the charge as a function of the capacitance and the voltage drop?
And multiply the capacitance by the voltage.
Exactly. What's our voltage drop again?
It is 8 volts.
So what is our charge?
I have 213 microcoulombs.
213 microcoulombs?
Yeah.
Sounds about right. Is that the correct answer?
Let me see. I have to convert it back to coulombs. G equals 2.13 negative 4 coulombs. Oh. Yep. That's correct.
Yep, to be correct.
Excellent.
Because I just
Excellent job.
Alright.
And then
I have a
obviously,
better...
literally it's just breaking down everything step by step, understanding, okay, initially capacitors act like wires. After a long time, they're an open circuit. And then when we disconnect the battery, what do the capacitors initially act like?
They act like batteries themselves and provide a charge or create a current through the circuit.
And then after a long time,
they die.
They die, exactly. And they just act like a wire again.
Yep.
So that's pretty much it. Sort of, honestly, not too complicated. It's one of the few things in this class. You haven't been coming to most of the sessions, but one of the things I've sort of, it's been the running joke so far this semester is, Roger, what's the one thing I've said the whole semester?
nothing makes sense in physics.
Exactly. Nothing makes sense in physics. Nothing in physics makes conceptual sense.
Oh, hey, Roger. Thanks for help on that assignment.
You're welcome.
Yeah. So I'm going to go ahead and wrap up the session here. Thanks, guys, for coming. Hopefully, it's helped out a bit. And good luck studying for the quiz tomorrow. And another session, same time on Sunday, going over tomorrow's material.
Yeah, just hope I can get the right hand all set up and down, because if anything, I feel like that would be the major reason why I might not do well in the quiz, because of that.
Yeah.
I didn't do well in the last quiz because I changed one of my answers at the last minute. And it brought me down to 8 out of 12. So,
Ooh.
yeah.
All right. Well,
Not feeling too happy about that.
as always, tomorrow and the next one.
Yeah,
I
honestly almost got the 8 out of 12 too. Then I noticed one of my mistakes, and then like the mistakes I made on both of the questions, and apparently I got the perfect A on that.
Yeah,
it was close. Oh, it was honestly close. I almost made one of them was a math mistake, and the other one I just